In this chapter, we're going to introduce differential equations, which is going to be a big section over chapter 9. In the first section, we're going to just introduce differential equations as a whole. Then we're going to think about mathematical modeling and introduce these two kind of ideas. So let's first introduce these concepts. A differential equation is simply going to be any equation that has a derivative in it. We've already dealt with plenty of differential equations in calculus. We just haven't called them differential equations yet. Now we're going to see some very simple differential equations that we've seen before, and then we're going to expand it to many different kinds of equations that we may not have seen before. A mathematical model is something that we've also dealt with a whole lot, and that's going to be an equation that represents some real life situation. We often think about application problems, right? We're given some mathy idea like derivatives or limits or some algebraic thing, and we apply that to some real life situation. The equation that we may use is called a model, or modeling a real life situation. Many real life situations use derivatives and can be thought of with derivatives. So therefore, a lot of differential equations can be used to model real life scenarios. And this really applies to basically any field. Differential equations can play a role and do play a role. So to start, let's look at some very simple examples. The first example is a child has an allowance of $2 a day. We're going to write a differential equation that gives the amount of money the child has. We're going to call that value m after t days. Note that this is a very simple example, but we're going to get harder on the next page and then in the next video as well. So to think about this, let's think about a little chart here. So let's think about the value of t and the value of m. So we're going to think about t when we have 0, 1, 2, and 3 days. The child starts with no money. After 1 day, he has $2. After the next day, he gets another $2. That's going to be $4. Then he's going to have $6 and on and on and on. And we can see that what's changing here each time is we are adding $2. And that's the information that we want to figure out. This is representative of the derivative, how the function is changing from one spot to the next. So just to write down the differential equation here, we have that the derivative d dt of m, we're going to write that often as dm dt. We could also think about that as m prime, or we might write this as m prime of t. So all these things are the same. That's going to be equal to 2. That the derivative is equal to 2, that's how much we're changing each time. So to kind of put it just all together, we're going to often write this as dm dt is equal to 2. And that's our differential equation. It's an equation, it has a derivative in it. That's all we need, and it's a very simple one. Note that in this example, we can actually do better than that. We can actually get the actual function itself. It's not that hard to see. We could say that m is just equal to 2t. Right? We can even think about it as m as a function of t is equal to 2t. But we can also see the relationship between functions and derivatives here. We know that the derivative of this function is just 2. So we're starting with a simple example just to get our bearings, but note that the differential equation here is not necessarily super useful. On the next page, we're going to see an example where the derivative is really easy to understand. The actual function itself is much more complicated. So that's when we're talking about population is often a good example, but we're talking about something growing at a rate proportional to something else, or maybe declining at a rate proportional to something else. So here we're going to think about rabbits, the population of rabbits, and it's going to grow at a rate k proportional to its current population. We're going to write a differential equation that models the population of rabbits after t days. So what this is going to look like is we're going to have the derivative of p with respect to t, that's dp dt, is going to be equal to this k, that's our rate, times the population. That's what it means to be proportional to something, is we're going to multiply those together. So this k is representative of our rate. The p here is our population at any time. Now, what's different from the last example is that it's not going to grow the same amount each day, right? It's going to grow a little at the beginning, and it's going to grow a lot at the end. What this function is going to look like, the actual function p, is going to be some kind of exponential function. The population is going to get bigger and bigger and bigger. It's going to blow up. And we're going to see that in the next example at the bottom of the page here. But again, this idea of proportional to its current population means that if the population is really big, we're going to add a lot of stuff to it. If the population is small, we're going to add just a little to it. And that should maybe make sense if we think about rabbits. If there's a lot of rabbits multiplying, you're going to add a lot of rabbits. If there's 2 rabbits multiplying, you're going to add a lot proportional to its population, but not a whole lot in terms of numbers. All right, so now let's look at a specific example where we can kind of put some numbers to this. Let's say the population doubles every 10 days. Let's find the constant of proportionality, that is k. What is this rate that we're looking at here? So again, let's set up a table to kind of see what's going on here. We have t, we have p, and we have first day. Let's assume we start with 2 rabbits. You got to start somewhere, and that does change the values here. So we start with 2 rabbits, and we're going to go along each day, but then eventually when we get to 10 days, we're going to double the amount of rabbits, and we're going to have 4 rabbits there. Then we're going to go to 20 days, and at that point, we're going to double the amount of rabbits again. After 30 days, we're going to double the amount of rabbits again. After 40 days, we'll double. And here's the idea that after a certain amount of time, we grow at a rate proportional to the population. We start adding more and more and more at the end. So again, we are not adding the same amount every time. We're multiplying the rate here by something. And what we're actually multiplying by is we're multiplying by 1 plus some number. And that number is going to be our k, to go from one spot to the next. And how we're going to solve this, just think about this, is that we know that to get from 2 to 4, we are multiplying by 2, right? That would be kind of our rate that we're looking at. We're like, so we could say that this is like multiplying by 1 plus 1. We could think about this as 100% growth after 10 days. K would be equal to 1 here, but that's in terms of 10 days. We also need to kind of take that into account. So this is kind of not really what we're doing here. Our K value is going to be that value of 1 corresponding to 100% growth divided by 10, because every 10 days we have that. So our differential equation here would be dp dt is equal to 1/10 p. We're not going to focus a huge amount on finding the value of k, but just to kind of show you where this is sort of coming from and what it means to grow proportional to its current population. So again, this example is maybe useful to understand what's going on, this is not going to be our focus on this chapter. All right, thinking about differential equations and modeling, let's think about what this actually means in real life situations. So we have this population of rabbits, and we were saying that it doubles every 10 days. So the graph of this population would look like, again, it would just exponentially get bigger and bigger and bigger, the actual population function. Right, here's T, here's the population. We kind of plotted some points at the beginning. This would be some exponential function. We'll learn how to kind of find that later on in this chapter. But in the meantime, we can just know it's going to exponentially grow. In real life, that's not what's going to happen. At some point, the population cannot double every 10 days. It's going to have to slow down at some point. And a more real life situation here has to do with something called the logistic equation. So a good way to think about the logistic equation is to think that these rabbits live on a small island, right? And there are some logistic constraints that prevent the rabbits from growing without any bounds. There's not enough physical space for the rabbits to just multiply forever. There's not enough food on the island. There may be predators on the island that prevent the rabbits from growing a certain amount, as well as a host of other things. So this limiting factor, that's what this L is actually standing for, is limiting factor, is going to be, at some point, that's as big as the population of rabbits can really get. And a simple way to model what would actually happen is this logistic equation given by the derivative. So the derivative is going to be given by this K times P, that's similar to what we had before, times something about this limiting factor, L minus P. We can kind of see in this graph what's sort of happening. We have at the beginning the same exponential growth that we had before. But then it's going to trail off and it's going to approach that value L. And that's what that L minus P is talking about. It's kind of like an inverse exponential graph there. In the next video, we're going to focus a lot more on the problems that we're going to be focusing on. The point of this first video is to introduce us to what differential equations are. Here's an example of a differential equation. It's a derivative in the equation, and it gives us information about the problem. The actual function here, right, the actually write what is P would be much more complicated. Much more complicated to write that down. The derivative gives us a lot easier information to work with. We also wanted to think about some specific kind of things we're going to look at. We're going to think about growing at a rate proportional to something, and we're going to think about growing at a constant change each time. And often we're going to combine those two ideas, and we'll see that in the next video.